Okay, welcome everyone. This is the Redis talk. We're going to look at how to optimize your Redis application, from a performance point of view, from an SDK point of view, from an application point of view. My name is Elena Kolevska, or Elena, same thing, it's okay. I'm a software team lead at Redis. I lead the client libraries team. A few of them, so Redis-powered, Redis, Node Redis, IO Redis, and P Redis are on my team, and my colleagues have the rest, like the Java stuff.
And my name is Paulo, and I'm a performance engineer at Redis too. So yeah, that's it.
That's us. Okay, so what's the idea of this talk? Well, you all use Redis, right? You know that Redis is really, really fast. Redis is blazing fast. But I mean, you as users, you don't care if Redis is very fast. You want your application that connects to Redis to be fast. And like from Redis to your application, there's a bunch of stuff that can go wrong. And sometimes like good or bad configuration can make or break your whole system. And we've seen a lot of cases of that. So what we're going to do, we're going to have a little imaginary startup.
Of course, and we all know that cats are the reason for the internet to exist, right? So we are developing a cat walks as service application, and then we just have three or so features. But yeah, then we'll deep dive on those features, and with the help of Elena, we'll try to optimize it and see what we can do.
Exactly. So what are we going to do here? We're going to start small. We're going to develop an MVP just to see if people even like our, you know how startups work, like you start small, then you ship it, you start getting reactions, right? And then you start to collect metrics so you can analyze, right?
Yeah,
and then
Elena, I think you have a typo there, right? So on the C point?
No.
No? Yeah.
It's metrics, right?
Okay. No.
I do have a typo.
No.
Okay. Okay, we collect our metrics, and then we're going to go ahead and actually evaluate the performance so we can go ahead and optimize our code. We can go ahead and optimize our code. And then you rinse and repeat, of course.
So, okay, we'll start with the feed. So we have users, and those users follow some cats, and we are interested in seeing what cats they follow, how many visits each cat has, unique visits, and that's basically it. Then we can also see the cat profile with the details, and then once we visit that cat profile, we need to increment to keep track the unique visitors of that cat, right? More or less aligned? Yeah. Okay, so how did we model this application? So we have hash that stores all cats. So we have an hash data type that's under cat and the cat ID. And there we store the ID, the name, birth date, so on and so forth. Then to keep the set of cats a user follows, we have a key that under the user ID key, we keep the cats, he follows, okay? And then for the unique visitors, we keep a set, okay? The set that data type that as the uniqueness property, right? So we don't have any duplicates inside a set, so we keep the visitors, the unique visitors, inside a set for each cat. That's more or less it.
Quick show of hands, who here uses Redis with like more than just strings, get and set? So you're familiar what sorted set is, more or less? More or less, good. Okay, so we're together. So as Paulo mentioned, we're just building a little Flask application here. One of the endpoints is we want to view the cat. Obviously, this example is simplified, so it's a good thing to show on a screen and on a conference, right? So getting the visitor ID, for example, usually you would get this from some kind of a session, after some kind of authentication. We're just getting it from the query parameters for now. And then we have a few queries here. When I say queries, I mean like we go to Redis to get our data. So you get that age get all. We go and get everything that's stored in the hash about that cat, right? And then we go to the set. So we issue the scard command, which is O of 1. So it's like light, fine. No matter how big this set is, it's always going to be constant, right? So that's already our second query. Here we get number of unique views. And then as a third query, we go ahead and actually update that set that stores all unique views with our own visit. Okay, so we get all of that, and we return the data. And then the next one is actually the feed that users are going to see, like with all the cats they follow. And here there's a little bit more work, right? But we do more or less the same. Before we get every cat's data that's here as part of this loop, first just we're going to go to our sorted set, get all the cats we follow, and then we're just going to go through each and every cat one by one and get all the data for every cat. Great, so far. But
okay. Yeah. So if a user follows no cat, the latency is around 13 milliseconds. The problem is, okay, once we start following more and more cats, we see the latencies increase, right? So instead of 13 milliseconds, we start to experience 200 milliseconds, and the guy that uses the catwalks the most is experiencing 1 second latency just to get the feed. So what may be wrong here, and what can we use to try to figure out what's going on? Okay, so I request Elena to instrument her application with OpenTelemetry to collect some traces. And here is what we see when we call the endpoint for a user that follows no cat. So we have a single endpoint call. So here is the API call. And I don't know if you can see, but here we have the Z-range call to get the set of cats that we follow. Okay, so this is taking around 11 milliseconds. Okay, we are okay with that. But then we move to the endpoint for the user that follows 10 cats. And we see that this request is taking the 200 milliseconds. And it starts with the Z-range query, but then we have a sequential call for the age mget to get the fields of each cat, and the scard to get the number of unique visitors. And we keep doing this for each cat in a sequential manner, right? So that's a problem. Okay. Once we hit that point, the endpoint of the user that follows 50 cats, we have the same behavior, but multiplied by 50 cats. Okay, so we have a problem here, right? Just by looking at the latency, we can see 1 second is not clearly what we expect.
Yeah. Okay, so then we go back to the code. We know what are the culprits: the HMGet, the repeated Z cards, and like the S card and the HMGet are our culprits. We go to the code, and of course we see, yeah, indeed, well, they're in a loop for like, if we have more cats, we're gonna have to go and do this 50 times 2, 100 network calls to Redis. Well, sure, fine, but we can do much better. Even 1 second is not that much, like their relational databases that have this kind of latency, but this is Redis, and we can do much better than that. So, ideas? Yeah.
It depends. You can fetch all the list of cats. This is the most simple. You can fetch all the list of cats and then to iterate them within your code.
Yeah.
It will not be the most performance-wise. It will be better than going one by one.
Exactly. We like fetch them all together instead of sending all of these network requests one at a time. So in the world of Redis, that's called pipelining. Okay, so what's pipelining here? What we have right now? We have ping pong, ping pong, ping pong, right? Request, response, request, wait, response, request, wait, response, right? From the client's point of view, all of this network round trip type, that's the most expensive thing in your system, right? If you think about it, every time you lead your machine, your process, you go across the network, that's expensive. So let's try to eliminate that as much as possible. What Redis allows you to do is do something called pipelining. With this pipeline, you send all of these commands as one thing. You send it in a single network request, and then you only have one network round trip time instead of 100 for 50 cats, right? How does that look in code? It's something like this. Now, so this is the first point where I'm going to call your attention on knowing your SDK, know what Redis and also your SDK can do for you. Because the SDK supports this out of the box. You don't have to think, okay, how am I going to chain, concatenate, or like, what's the point? No, you don't need to know the exact specifics of how this is implemented in Rust, right? That's the reason for the existence of an SDK, and we try to build good user-friendly, developer-friendly SDKs. So on the Redis instance, you just call the pipeline method, and then instead of calling the commands directly on the Redis client instance, you call them on the pipe, right? Pipe, HMGet, scard, and so on. What Redis is going to do in the background, it's not going to send anything. So nothing leaves the machine here or here. It leaves the machine here when we actually execute the pipeline. Until then, we just go ahead and create a little queue. This queue is just the concatenated. So we have the queue. In the end, we concatenate everything. This is what Redis expects, like just the carriage return, the rn, rn, rn. All of these commands here are going to look something like this. We send this big concatenated string to Redis, and Redis is happy. And I say, not just the application is happy, but Redis is happy as well, because with this, you're also actually improving the performance of Redis itself. For Redis, it's easy and it's fast to just go to memory and work with data, right? But it costs more. Again, we're talking about cost here, right? And it costs more to actually go and read from the socket. So if you are like forcing Redis to really move back between the data line and the socket line like 100 times, it's going to complain. It's not going to complain, okay, but you're gonna feel that in terms of latency and throughput for sure. If you said, okay, you read all of these 100 commands once, you only read once from the socket, Redis is much happier and it purrs. Sorry for a stupid pun. So it gets much better throughput, right? Okay.
And yeah, just like Elena was saying, we can see the results here, right? So if by applying pipeline, we go, okay, of course, the user that follows 0 cats, the latency is exactly the same, right? Because we aren't pipelining at all, because we don't have any HMGet or scard, because we aren't looping. But as long as the user follows some cats, the improve in latency is higher and higher, right? So here we can see that the latency is more or less equal. So regardless the number of cats that we follow, yeah, we experience more or less the same latency. So 22 milliseconds, 23 milliseconds for 50 cats. Okay, so if we refresh the whole thing, then we should expect more results. So the gain is pretty clear, right? So 1 second to 23 milliseconds. But we can go even further, because we noticed while we were doing this that the application was deployed in Dublin, but the database was in London. So even that round trip that we were doing, so of course now we are just doing 2 round trips, right? One for the Z range and the other for the pipeline request, for the old request. But even those 2 trips, we are paying 10 milliseconds for each. So if we collocate the application in the same region as the database, then we expect that latency, that round trip, to be much lower. And that's what we did in the next slide. And from the 1 second with pipeline and the database on the same region that the application, we are now experiencing 5 milliseconds, right? That's the refresh latency of our monitor. So yeah, we do see that, yeah, fetching 50 cats, it's really, really fast with Redis, using pipeline and of course collocating in the same region. Okay, so what we did so far, we used pipeline to avoid multiple round trips, and then even with much low round trips, we want to collocate both application and the database at the same region to pay less for each round trip. Okay, but now we have the application all tuned, but catwalks was referred on a famous talk show, and the users that hit our application spiked. And yeah, we got a problem. So our latencies that were really, really low started to increase with the number of operations. So here we see the number of clients that we have, in red the latency, and we see that the throughput, okay, the throughput, I can serve more requests per second up to a certain point, and the latency then starts to spike to higher, and we have a problem here because we want to serve more and more users as they arrive, right? So maybe, yeah, we should tune our database.
Exactly, yeah. So we could see that our Redis cluster here is struggling. Sorry, our Redis instance here already started struggling, right? We could scale it up, like add more memory, more CPU. More CPU wouldn't even help that much, right? Because Redis is single-threaded anyway. But you could theoretically, right, try to pump up your machine, beef it up, scale it vertically. Up to a certain point, you're going to start hitting some limit. And first limit, in this case, probably you're going to hit is the CPU limit, even though that's very hard to do with Redis. But at a certain scale, you start to hit that. If it's not memory, it's CPU. Okay, so then if you still plan to grow, and catwalks.io does plan to grow, you have to have different strategies, not just the vertically scaling one. And this is a common thing. It exists, right? In tech, in distributed systems out there, it is possible to get your data, split it in different shards, partition it, put it in different places, and then it's more manageable, scale horizontally, right, or scale out. It's not that easy to do with relational databases, although people do it, but it's actually much simpler to do with key value stores. So if all of your keys, all of your data is unrelated, and you can just grab a bunch of keys, throw it somewhere, grab another, throw it somewhere else, and it doesn't matter where they land, right? Then it's much more easy to just grab that data and split it into different shards or partitions or nodes, whatever term you like to choose. So obviously this is great, because then instead of paying like very customized, very expensive beefy machine, you pay a few commodity machines, so it's cheaper, it's easy, you can easily buy one, you can easily replace one. You can scale out, as we said, and usually like kind of close to linearly. It's never linear scaling, right? But theoretically, it, I guess, could be or close to linear. But there's drawbacks, of course. While before, you had this beautiful, simple, single machine where everything lived, all of your data was here, it was very easy to connect to it, you know its address, everything lives there. Now you have all of these guys, and you have to know where the data lives. They have to coordinate between each other, they have to know where the data lives. So from a beautiful, simple monolith, you've gotten yourself into the distributed systems world, and things here are different. It's just a whole new level of headache, but also scale. Okay, the way Redis does this horizontal scale, so our scaling out solution is called Redis cluster. Who here knows Redis cluster? You don't count. Okay, so a few people already know and have worked with Redis cluster, and interestingly, we kind of get this feeling usually from audiences, stuff that people don't know enough about Redis cluster. I don't know if that's because, Redis usually is quite fast, but and maybe you don't need that much, but there is so much more. Like if you have more data, this is actually a pretty easy solution. It's not a managed. Sure, you have to know some things. You have to study documentation a little bit, right, in order to run this yourself. But there's managed solutions as well. So what is Redis cluster? Let's just try to explain this in a very simple and just very high-level way. This sample example cluster of 3 shards. What is a shard? A Redis process, just like before. It's the same binary. You just configure it to run differently. You tell it, okay, start up, but know that you are part of 3. You're one of 3. And I say 3 here because this is an example of 3, but it should always be like 3 or 5, always an odd number of specifically master shards, actually in Redis cluster, not elements in general, but specifically master shards. So then you tell each of these guys that they're part of a system and they have to figure it out, align. You have to talk to each other. You have to have consensus on what's the status in this cluster. Are you up? Are you down? Are you accepting requests? Are you not? Like what happens if 2 of you die? What happens if it's not accessible but you have no idea if it died? Am I actually the one who died, who got network separated? Like all those beautiful distributed system mind teasers, right? So they have to coordinate. Great. So then they do that. Redis cluster provides this, like there is a what we call it, like this full mesh network between all the shards that communicate through a binary protocol, and all of that happens transparently. The user doesn't have to know anything about it. He just say, okay, you connect your cluster, and that's it. Everything else happens automatically. Now, the problem then becomes like, how do you shard the data, right? Where does the key live? So if I go back here, like if I want to save the key full, should I connect here, here, or here? Okay, I'm going to connect here. I'm going to choose randomly. I'm going to connect here. But then another client might choose randomly to connect there, and the key is not there. Well, there has to be some kind of consistency, right? And the only thing we have to go about is the key name. So that means that we have to find some kind of way to decide where to look for a key only based on the key name and nothing else that's variable, at least. There's one constant involved, but okay, so there's multiple ways in the world, in our beautiful tech world, that people do that, like consistent hashing and logical sharding. What Redis does is this kind of virtual sharding thing. So it basically says, well, if I go and I work with the specific number of shards, let's say I want to have 3 shards, that's great. I can do that. I can work with some modulo thing, right? Divide everything by 3 and decide on which shard a key is going to go, which is going to work great until I want to change the number of shards. And then I have a variable name in that little formula that I have to decide where does the data live. I can't have a variable name. It has to be only the key name and nothing else. That's variable. So what Redis does, it splits everything, like pre-splits, like creates this virtual space of 6,384 hash slots, which is nothing more than a little virtual box. Okay, just a little box, and you put keys in it. Like if you had a chest of drawers, that's Redis, and a bunch of drawers that are different virtual box, and your keys are your socks or whatever. So this is how we have to view these little virtual hash slots. They don't exist. It's just like a box that encapsulates something. Okay, so if we had a cluster of 1, it doesn't make sense, but if we had a cluster of 1, that means that this would be the Redis process. All of the keys, all of the hash slots live on the same shard. So far, so good. And then this is the little box. It's going to contain like keys. Every box contains a key. And then if I want to reshard and actually create a cluster, this is a cluster of 2. You shouldn't have a cluster of an even number of elements, but it's fine because this is just our example. Then I got part of the box, like half of the boxes, and I moved them here. They kept their keys. Every box kept their keys, okay? So this is it. Let's say we split our data. Now we have 2 Redis processes. We have a cluster. We connected them, right? We moved the data. Those are just simple commands like Redis cluster migrate slots, so that's easy to do with Redis. And then what happens? We run into this error. Why? What does it say? Well, it says that this command you tried to run, hmget, caused an error, moved. The data moved, and it's now at that IP address. Why? Well, because our client, as it is, without changing anything, only connects to that shard over there, which was the original one. It doesn't have yet any connection to the other shards. So what should the client do? Should it try to parse the address from there, or how are you going to go follow that key, right? It could happen, you could try and parse the IP address out of there and then connect again to it, but that would be so wasteful. 2 network round trip times doesn't make a lot of sense. Very, again, expensive, very wasteful. So that's why, once again, you have to know your SDK. You have to know that actually there is a thing called Redis cluster. So you have the Redis client and Redis cluster client. So the SDK already does that for you. And then the cluster is going to know that, okay, well, I'm going to actually keep connections open to every shard, right? And then I see where I need to go. How do I see? How do I know where do I need to go for the key foo or bar or whatever? Well, that little function that we said, okay, it has to be, we have to know how to get from a key to a hash slot name. So that's deterministic, and it's the same. You can choose a single hash function that you use on the server and on the client. It's deterministic. It's going to be the same no matter who runs it and where. You're going to get the number. So actually, as a client, when you say, okay, set foo, I can run this algorithm locally on the client side and get this hash slot number. How do I get from the hash slot number to the address of the shard? The cluster library can issue this cluster slots command every time it initiates it, every time it starts, you initialize it. You give it one address of one or multiple, at least one, of one of the Redis instances. It's going to ask it, hey, give me, discover all the other shards. It's going to get that. It's going to store it locally, a little cache. It's going to keep some kind of map like this where it tells it, well, the first range from 0 to 8,000 is on this IP address, 8 to 16,000, this IP address or port, and this is where you get them. So then when the client needs to do a set, it does this little process, gets to this number, compares it to this range, and finds the IP address of the shard where it needs to connect to. So you see, we went from something like this, where you connect to the wrong one, and you don't know, like Redis gives you a hint, okay, this is where it is. But you don't have to follow that. You can do this proactively yourself, and you've just saved one network round trip time, at least. Okay, I think that's enough about the cluster theory. Sorry about the little digression here, but I think it is important because people, like, as I said, sometimes it feels like people are scared a little bit. And I admit I was, like, when I started with Redis, I also was a little bit scared of Redis cluster, but in fact, it's really not that complicated. In terms of code, the only thing you have to change is, so instead of instantiating Redis.Redis, you instantiate Redis.Redis cluster. Obviously, so it's not type safe, right? So, but the API is going to be the same across the two libraries, and in the rest of the code, you won't have to change anything because the API for Redis cluster is like a superset of this one. It just has a few more cluster-specific commands.
Okay, thank you, Elena.
Yeah. Yeah. Yes. But I'm going to challenge you on the term database. What is a database then? When you say, you're right, and I'm joking. I know this is in the documentation. It says select database, select DB0, select DB1. That's not actually a real database. That's just, a logical namespace. So it's, in fact, just a prefix of some kind. But you don't have like separate configuration files, separate authentication, memory limits like max memory. It's actually it's the same database. It's just that it's unfortunately it's something historical. And Salvatore Sanfilippo himself actually said, "Oh yeah, I regret that I did that."
Okay, so a small step in the code, but a big step on the performance, right? So here we are seeing on the left side of the screen the performance, the number of operations per second that we could reach using a single instance and the latency. And now with a 3-shard cluster, the throughput is much higher, right? So instead of doing, I don't know, 80K operations per second, now with 3 shards, we are capable of doing 150K operations per second, keeping the same latency, okay? The good news is that if we need to scale further, we just need to add more shards. And the code is exactly the same, and as you see, you just need to use that Redis cluster client variant, right? Okay, so we have this solved, but now Maverick comes and he signs up on our application, and with it, we notice a high memory usage on a specific shard. So we had one shard that the RAM, the memory usage has spiked. So to try to figure out what happened, we used this Redis CLI -- keystats utility that basically Redis CLI is our common client, right? So the command line client, and it has this tool, keystats, that basically loops throughout all the keys and produces some metrics. So how much memory are being used by each key? What are the top 10 keys that take the most memory? And here we can see that Maverick, this guy here, is taking almost 1 gigabyte of memory just to store the unique visitors. So do you remember? So once we visit a cat profile, we need to keep track of how many visitors, different visitors we had. And we are using a set, right? So that magic data structure that keeps track of unique records. Okay, but now, and we only expect Maverick to rock even more. So yeah, how can we deal with this?
Yes. So we already did a bunch of optimization, right? In terms of system topology, in terms of latency, in terms of SDK proper utilization. And here, it's none of those problems. It's something else. But we can now move into the data modeling itself, so which can really also help you very much optimize your application. If this were some kind of financial application, that would be it, right? We have to have all the data. We have to have a list of all unique visitors in order to know. So we have to have them saved, so in order we can know, okay, if a new one is coming, how can we know if it has been there before? Well, we have to compare. But because this is something lighter and something that can be relatively approximate, we can actually use my favorite probabilistic data structures. I love probabilistic data structures because they can really help you with so little effort, and they're just very cool. Once you start looking at their internals and how they're built, it's just so smart, makes you want to use them everywhere possible. So that's why you need to also, like you need to know your SDK, but you need to also know, get very familiar and intimate with all the existing Redis data structures. And Hyperlog has been in Redis for many years, but there's also Redis Bloom, there's tdigest, there's Cuckoo Filter. All of them are nicely documented in the Redis docs. So if you talk about Hyperlog, like we already, no, this is the back one.
Yeah. So here we are seeing the code, right? So we are inserting for each visit, the
in the
visit.
set, exactly, the unique members. Sorry, I skipped that a little bit, but I talked through it anyway. So this is the culprit. This is our key that exploded to 1 gigabyte, a 1 gigabyte single key. And we can introduce the hyperlog log. A hyperlog log is, as I said, a probabilistic data structure that provides the cardinality of a set, but without storing all the elements. So it does some magic inside. It's pretty cool. You can read there's a blog post from Salvatore, or you can read the comments in the Redis core itself, the code itself. Okay, so basically what happens, you just shove stuff into it. You say, okay, just add this member to the hyperlog log, and then tell me what's the cardinality. Tell me how many. So you add with pf add, there it is, with the pf add command, you add stuff in it, and you get stuff out of it with the pf count command. The cool thing is that this key is never going to go beyond 12 kilobytes, below or beyond. So it's actually going to be fixed, 12 kilobytes forever per cat. So we had a linear growth with every new follower that was only going to grow. It never goes down, right? It only goes up with every new unique visit. Those keys were growing. But now you have a fixed 12 kilobyte data structure in memory, and that's it. So very predictable.
So instead of having 1 gigabyte of memory being used on the set, okay, we are just paying 12 kilobytes,
yes.
okay, with an error of margin
0.81
below 1%.
Exactly.
Okay.
Exactly. And this is fixed. Like, this allows you to plan, because you cannot predict how many users are you going to have in a year, or if someone else is going to explode again and become insta-famous, or then you have a big influx of users, a unique visit of a cat. That thing you cannot predict, so it's difficult to plan for that, right? And especially if you have to store something that's, memory heavy. But with this, you can easily predict, okay, I know how many cats I have, and I'm protected from spikes. Relatively, right? Everything is relative, but at least protected in this part because it's fixed, 12 kilobytes, and that's it. So you can plan for the future. No one's going to get woken up in the middle of the night. Which matters, right? Quality of life. Okay, so now, I don't know if you noticed, but something interesting where you also have to, again, know your tools, know your SDK. This thing here, when it was an S card, was inside of the pipeline, and now it's out. Well, that sucks a little bit, because now we have more calls, right? When we look at that feed page, we're going to have one extra network call. Why? Why did we have to do it? Well, we had to do it because this command, pf count, if you try to put it here in the pipeline, it's going to give you error, hey, I can't run this command. This is the prohibited command to run in a clustered pipeline. When we first saw that, I was like, wait, why? Why? That doesn't make any sense. We can do distributed pipelines, which is, technically speaking, like if you really want to be precise, not completely correct because of ordering, right? But you should be able to do this. If you already have it, why not support this? Well, I started digging out a little bit and realized the pf count command is actually a variadic command. So it accepts key 1, 2, 3, and then Redis actually can stack those 3 different HLLs together, one on top of the other, and estimate the cardinality of all of them. Not a simple sum, but the cardinality across all of them, like a union. So that's why this was rejected. Well, I can't do that on a cluster because then I would have to, if you send me 3 keys and they don't live in the same hash slot, I'm going to get a cross slot there. So that's why the original maintainer or contributor who contributed this command just opted in to return an error. To return an error. So, Ricardo, estou sem mic, mas tudo bem, consigo gritar. Okay. So they opted to just return an error. And again, this is again when I'm going to challenge you. Read the code. Just click through in your ID, see what's up. Not always everything has to make sense. And this was a community-maintained library for many years, for over 10 years before Redis, the company, took it over. And now we're responsible for it. We maintain it, and we want to give really the best developer experience. But this is something that was there before our time. And if you find something like it, challenge it. Write an issue. Go to the Redis-powered. It's very active. The repo is very active. We have an amazing maintainer, Petya. You're gonna meet her. She's gonna respond, and she's very quick to respond. And if you feel extra nice that they send a PR, even it's just Python after all, and you don't have to do everything, right? When you send a PR, even maybe just write the code. We're going to say, okay, tests are missing, but I can help you. Hey, would you like to do it? Let's do it together. We guide you through the process. And that way you get to contribute to open source, have something nice on your profile, and everybody wins. Everyone's happy.
Thank you.
I think it's your turn.
Okay, so what we did so far. We started with pipelining, right? So instead of doing a bunch of round trips between the app and the database, we packed together everything we can so we can pay less round trips, right? So then we saw that even though we have much less round trips, we were paying a lot, 10 milliseconds between them, for them, because the database was living in London and the application in Dublin. We put both application and database together. Then we moved to Redis cluster because we had a bunch of new users coming in. So now we introduced the concept of sharding, and now we have multiple shards taking care of the requests, and we can scale horizontally. So if we need to serve more and more clients, we just need to keep adding shards. And then we saw the hyperlog data structure that enabled us to reduce a lot of memory usage, right? Okay, so Elena, I don't know if you have more hints on how to configure the clients, so other use cases.
I do have actually a few more things prepared, not too much, but I would like to invite you, because this, we have 6 minutes left. So you guys choose if you would like us to keep on going, mention a few other parameters that are cool, that are interesting to know about, or you would like to ask questions. You can also talk to us after. So in a way, you could get both. So we keep going? Okay, let's go. So this image that I showed here before, it's not completely true, okay? So I lied a little bit. I didn't maybe lie, I oversimplified it a little bit. So it shows that the client keeps a connection to a shard, which is correct, but it doesn't keep one connection, it actually has to keep multiple connections. If you have a single Redis client instance that's being used in a multi-threaded environment, you're going to get different threads trying to compete to get on the connection, to get on the TCP socket in order, like waiting in line, so they can send their command to Redis. And that can and will become the bottleneck, right? Because the TCP connection itself, by definition, is a bottleneck. So what the Redis client does actually, when it instantiates, it actually opens a pool of connection, a bunch of connections that are already prepared and ready to go. So there is no contention here. Different threads can use different connections at the same time in parallel. And then it can scale dynamically as well. So the more you request, the more connections the library is going to give you. And this is controlled through this parameter, max connections. So when you instantiate your, and this is the point of the next 5 minutes, is like when you create your Redis client instance, go through the parameters. Don't go by default with the defaults. Até porque? Because, like, for example, this max, do you know what's the default value of this max connection currently? 2 to the power of 31. That's crazy. That value doesn't make any sense because Redis it's not even going to support that many connections if you're talking about a single instance. Again, that's some kind of leftover from someone in the past. If you want to go and do Git blame, you can probably find, but that's not the point, right? But I'm currently in the process of actually standardizing all the default values across all the different Redis client libraries because that's something we really need to do. So kind of trust by verified, but verified thing is same here. Don't go with the default values just because they're default. They're not necessarily the best values for you.
You mentioned you have like a general SDK app that has multiple UV card workers. Would you suggest we use like a single command that needs just the Redis output one time, or have one for each worker we have in our application?
So the question was, should we use the single instantiated client passed through different threads, right? Or start a different client in different threads? Depends. You could, so the client itself is thread safe. So you could pass the client to different threads and it's going to work because the pool is thread safe. So the client is actually always going to take a separate pool. It's prepared to be used through multiple threads, and that's the whole point of the pool in the first place, right? So it's going to depend. It depends how you want to manage, like if you want to configure them differently, if you have something else, like maybe you're going to use one client just for pub/subs, maybe you're going to just use the other one for data. It's going to depend. But in the end, like you would have probably a little bit less overhead if you use a single one with a bigger pool.
Okay, thank you.
I have another question, a follow-up. You mentioned that Redis is single-threaded, or it works on a single CPU. Why should we open multiple connections if it runs in a single, CPU?
Good question. Yes, good question, definitely. Because you remove the bottleneck, and Redis is very fast in reading, right? It reads, and it also has multi-threaded reading since a few versions ago, right? So it has multi-threaded I/O. Would you like to add something?
Yeah, yeah. I think that's it. So.
Sorry?
So when it reads multi-threaded, it's on multiple CPUs, or it's?
Yes, it does. So of course, yeah, the main thread is the one that is responsible to execute the command itself. But now we do support I/O threads, which are responsible for the I/O. So reading and writing to the socket. Now it can be done on separate threads.
Okay. Thank you very much.
Yeah.
Thank you. Anything to add about this?
Yeah, I think
this is good. So yeah, maybe set your maximum connections to something more reasonable, right? Otherwise, if your traffic really explodes, you might get every connection like what was it, 4 kilobytes of memory or 8? I don't remember, but every connection that you open, it does require some memory. So you might get into trouble if this is practically unbound. We have the socket keep alive, also another, we can let you go also, but maybe just two or three more. Socket keep alive is quite cool. Like if you have an application that doesn't have a lot of traffic, and not always, let's say during the night or something, and then you have a Redis that's disconnected for some reason, if you let the operating system do its work and send keep alive on a socket, it's going to close it. Instead, if that doesn't happen, if you have a dead connection and then the application comes and tries to send and that has to wait for it to time out, and only then you report an error, right? So if you set socket keep alive to true, this happens automatically for you, and then the proactive, like the reaction time to an error is much, much shorter. And speaking about timeouts, set your socket timeouts properly. And this is going to be very environment specific. I don't even know at the moment what's the... actually, it's none. It's not even set. There is no timeout in Python right now. But you should definitely set it. And it's going to depend wildly on your environment. Like if you are not co-located like Australia and London, then your timeout is going to be much bigger because it has to include like the network, half of the network round trip time, right? But if it's collocated, like even have it to something like 15, 20 seconds, or milliseconds, is going to be more than enough. And with that way, you can be faster to react to problems. And then the last one, set your retries. Sometimes there's going to be network glitches. There's going to be some like sporadic errors that are not like those repeatable errors non-repeatable errors that you shouldn't go ahead and try them again. But like network errors, some server errors are going to be great candidates to be repeated. And then if you go and set your retry policy, like you have different ones, you can specify how many retries, how many times you want to retry, like linear or exponential backoff, with jitter, without jitter. All of this can be configured in your SDK. And again, it's going to depend on how you use this. Okay, I think that's all we've got for now. I think we're pretty much on time. Anything else to add, Paulo?
No, yeah, I think, yeah. Thank you, Elena. Yeah.
That's it. Thank you all.
Yeah, thank you.